By now you're convinced, beyond any plausible doubt, that there is something called dark matter in the universe. What we've done is we've looked at the dynamics of bound systems moving under their mutual gravitational field. We've looked at galaxies, the rotation curves of stuff moving outside galaxies, and we've looked at clusters of galaxies, large samples of hundreds of galaxies, and thought about both what the galaxies are doing and what the hot X-ray gas in between the galaxies are doing. What we find, either way, is that you can't explain the motions that you see unless there's more matter in the universe than the stuff we can directly observe. So this should be evidence that closes your mind about whether or not there is dark matter in the universe. Except that, of course, as scientists, we don't like to close our minds until we really are as sure as we can possibly be. So in this lecture, what we're going to do is just to convince you again. We're going to give you a completely independent set of information that points to exactly the same conclusion, that in galaxies and clusters, there's much more matter there than the matter that we actually see. What we did when we looked at the motions of galaxies and clusters is really we were mapping out the gravitational field of those objects. So Einstein told us that whenever you have stuff in the universe, it creates a gravitational field. So we have a surefire way of finding everything there is. Just map out the gravitational field, use that to work backwards, figure out how much stuff there is in the universe. So we did that, but we like to do the same thing in a different way. We took advantage of the fact that particles, whether these particles are really individual particles or entire galaxies, move in a very determined way in the presence of a gravitational field. But they're not the only things that are affected by gravity. Even light itself is affected by gravity. That's part of the conclusion that Einstein was able to draw from the fact that gravity is the curvature of space-time itself. Nothing escapes gravity's influence, so even a beam of light passing through a gravitational field will be deflected. This process of deflecting light due to gravity is called gravitational lensing, and we can use it as a completely independent way to figure out how much stuff there is in the universe. So the basic idea is simple. You take an object, the object gives rise to a gravitational field, and you pass a beam of light past that object. What's going to happen is the attractive force of gravity will bend the light ray as it passes by. In an extreme example, it can bend it quite a bit. So here is an artist's impression of a gravitational lens that might be formed by a galaxy where the thing being lensed is a quasar. A quasar is a very bright nucleus of a galaxy, the center part of a very young galaxy very far away, giving off a lot of light. So they look like points to us, just like stars do. So quasars come from the words quasi-stellar objects, because originally they looked like stars. Now we know that they're actually galaxy-sized things in the very early universe. So you look at a quasar far away, and you look in many, many quasars, and you get lucky enough to find an example where there's a quasar far away, and in between you and the quasar is a galaxy, or a cluster of galaxies, or something like that. If the gravitational field of the thing that is in between you and the quasar is sufficiently strong, you can actually deflect the light from that quasar on both sides of the lensing object and get multiple images, 2 images of the quasar. So this is something that people have been looking for a long time, and in the 70s and then in the 80s, they began actually finding them. So you can find pictures of things that look like exactly the same astrophysical object very, very far away, and it's because there's something in between that is breaking up the image into multiple copies. You might ask, how do we know that these 2 images that look the same are really of the same object in the background? The answer is, of course, we can take their redshifts. We can find out how far away they are. If you find 2 objects that look the same, they're right next to each other, maybe there's a little fuzzy thing in between, and you measure their redshifts and they're equally far away, it's very likely that what you're doing is looking at exactly the same object. In fact, you can do more than that. You can be more precise, looking at the spectrum of light from that object, and you can really verify that they are 2 different copies of the same thing. So the reason why it's called lensing is because it's exactly the same kind of thing that you would get when light passes through a piece of glass that is not absolutely uniform. If you have a piece of glass that is warped, has different shapes, then the image that you see of something behind it will be distorted when you see it. You can do that correctly to make a lens that focuses on you or defocuses, but when you see any arbitrarily warped piece of glass, it will always give you distorted-looking images. It's the same kind of thing, except instead of a piece of glass, we are now looking through a distorted space-time, distorted by the stuff in between us and the stuff we're looking at. This idea of gravitational lensing, of light being deflected as it passes through a gravitational field, goes back to Einstein himself. While Einstein was working on Einstein's equation, when he was trying to derive the general theory of relativity, he was already thinking ahead. He was mostly coming up with the theory in his mind through thought experiments, but he was already thinking ahead to how will we know whether this theory is right? How will we test it against the data? Of course, we already had a theory of gravity from Sir Isaac Newton, which was really good. Everyone thought it was the best theory ever invented, and now Einstein is coming along with a different theory. There was already one piece of information that people knew about even before general relativity, which is that the motion of the planet Mercury around the Sun was not quite right. It was not quite moving in the orbit that you would have predicted according to Newton's law of gravity. So, what do you do when something moves in an orbit which is not quite what is predicted by Newton's law of gravity? You invent dark matter. And that's in fact exactly what was done. A French astronomer named Leverrier invented an invisible planet that was supposed to be existing between the orbit of Mercury and the orbit of the Sun. He called it Vulcan, and unsurprisingly, it was discovered several times. Every time it was discovered by mistake because it's not actually there. The idea was that this new planet was a mass that was distorting the motion of Mercury. It turns out not to be right. It turns out that it was in fact gravity that was behaving differently. And when Einstein invented general relativity, one of the first things he did was to test what the orbit of Mercury should be like in his theory, and he found that it agreed. This was, in Einstein's own words, the happiest moment of his life, when he realized that his new theory fit this already existing data. But he was also a good enough scientist to realize that it wasn't good enough to fit already existing data. You needed to make predictions for data that hadn't been taken yet. So as soon as Einstein invented general relativity, he realized that the fact that everything is affected by gravity means that even light will be affected by gravity. And this is something that Newton's theory didn't say anything about. So he was making a precise prediction that would be different in general relativity versus Newtonian gravity. However, the problem with this prediction was it was very tiny. The gravitational field from a star or from a galaxy, Einstein didn't know about galaxies at the time, he was thinking about stars or perhaps the sun. The sun is the closest thing to us that is a large, massive object, but still the gravitational field of the sun in absolute terms is just not that much. The amount of deflection that you get by light, of light by the sun, is a very, very tiny angle. And there's a more profound problem when you're trying to use the sun as a gravitational lens, which is that the sun is bright. So if the sun is sitting there and you're looking close by the sun, hoping that it will lens some object through its gravitational field, the problem is you can't see any other objects, you just see the bright blue sky behind you. There is one loophole to this problem, of course, which is the possibility of a total solar eclipse. If you're lucky enough to be in the right place at the right time, when the moon goes in front of the sun, then the sun is there, still gravitationally lensing things behind it, still deflecting the light of stars that are nearby, but suddenly you're not blinded by the sun itself. So if you take a picture of some stars in the sky, and then wait until a future moment when the sun is in front of them, and there is a total eclipse, and then you take a picture of those stars again, you can compare the image of those stars, their positions on the sky, with the sun there and without the sun there. If general relativity is correct, the gravitational lensing effect of the sun will distort the positions of those stars in your image on the sky. So fortunately for Einstein, he invented general relativity in 1915, and there was the perfect eclipse that was going to happen in 1919. Now, of course, 1915, most people in the world, when you ask what was going on in 1915, if they're physicists, they will say Einstein was inventing general relativity. Most other people will say World War I was going on. So World War I ended a couple years after Einstein completed relativity, and the eclipse came up in 1919. An expedition was launched to make observations of this eclipse by Sir Arthur Eddington, who was a British astrophysicist and a very respected scientist in his own right. So Eddington launched an expedition, went and took images of the stars in the sky before and after the sun was there, and he compared them. When he got back to England, they developed the film, and they realized that, in fact, yes, there was gravitational lensing of these stars. There was deflection of light by the sun, exactly as Einstein had predicted. So what you had was a theoretical construction by a famous German scientist being verified by an observation done by a famous British scientist, and it was actually taken at the time to be a very nice example of international cooperation among scientists. Even though these countries were on different sides during World War I, they still agree that space-time is curved, which is a good thing to agree on. It also was the thing that launched Einstein's celebrity. Back in 1905, when Einstein was inventing special relativity, he wrote many papers that made him famous in the scientific community. Everyone in 1915 appreciated the genius of the general theory of relativity, but in 1919, when Eddington showed that the sun was deflecting light, just as Einstein had predicted, it made the front page of the New York Times. The general public suddenly realized that Isaac Newton had been superseded as the leading person to understand how the universe works, and Einstein took on that mantle. That was when he really became a public figure and often used his public persona to good purposes. These days, we go beyond looking at just the gravitational lensing of the sun. We use gravitational lensing as a tool to weigh things. So the foremost thing that we're going to use it to weigh are, of course, clusters of galaxies that we believe are fair samples of what is in the universe. There is another use that I will mention just parenthetically. We'll get to it in more detail in later lectures, but that is to look for individual dark stars. If you have a dark star, some form of thing that is about the size of the sun, when I say about, I mean anywhere from 100 times the mass of the sun to 1/100th or 1/1,000,000th the mass of the sun, you can find those using their gravitational lensing effect because they move through the sky. So they're dark, but they're moving through the sky, and every once in a while they will pass in front of a visible star. You can see the effect of the gravitational lensing on that visible star. It's very tiny, and it's called microlensing. That's a way to find dark stars within our galaxy, and that's something that we're going to be talking about later when we're talking about what might the dark matter possibly be. For right now, we're trying to establish that dark matter really does exist, so we're going to use gravitational lensing to weigh clusters of galaxies. In other words, to map out the gravitational field of a cluster of galaxies in some detail. You can see, if you think about it, there is an obstacle to doing this that is not there for the sun or for these dark stars that you might find by microlensing. The obstacle is that the cluster of galaxies is not moving in the sky. Both the cluster and whatever is behind it are sitting there on cosmological timescales. So even if you see something being lensed behind it, what you want to do is to find out how much lensing there is, but you don't know ahead of time where the object was. If the lens was not there, where would you see it in the sky? You can't compare before and after images because nothing is moving. The universe is more or less static over these very, very large distances. So what you're trying to do is to figure out a way to measure how much deflection of light you really have, even though you can't first put the lens there and then move it. You just have to deal with the fact that it's there. Well, there's actually two different techniques that people have worked out to use to measure how much deflection of light there is. The first one was implicit in the first example we showed, the fact if you have strong gravitational lensing, if the lensing is so strong that you see more than one image of the background object, then you can figure out the angle by which it is lensed. If you have one object in the background, it passes through a cluster of galaxies and you see two images of it, then there's an angle on the sky that is telling you what is the angle by which the light is being deflected. That is called strong gravitational lensing and leads to some very pretty pictures that you can see how strong the lensing is of some background galaxies. The other possibility is weak gravitational lensing. And weak gravitational lensing is actually much more common than strong lensing. Strong lensing, you're very lucky to find such a good example. But weak gravitational lensing is just the idea if you have a cluster of galaxies, you have a bunch of galaxies in the background, they will all be distorted by just a little bit. If you only had one galaxy in the background that passed through the gravitational lens, you wouldn't know what it was supposed to look like and where it was supposed to be, so it wouldn't help you in figuring out how much lensing was going on. But if you have many galaxies in the background, their images will be distorted in a systematic way by the gravitational field of the cluster. So the fact that they begin to line up, not due to any intrinsic alignments, but because of how the light has passed through the clusters of galaxies, is going to be able to tell you how much lensing there was. And so both of these techniques are in fact going to be used. Here is another image of a cluster of galaxies. You can see a couple of visible galaxies in the middle, and then also up and to the right, there is a bright red object in this picture. This is an ancient star-forming region. It's an intrinsically interesting object all by itself. Forgetting about dark matter, just thinking about astrophysics. This is some proto-galaxy that is coming to life, bursting with new stars and giving off a lot of radiation. It is in the background of this cluster of galaxies. We can measure its redshift, we can find that it's far away, and you see that it's distorted a little bit. You can see that it's aligned in a certain way that is sort of circularly wrapping around the cluster of galaxies. So let me show you this animation. This is an animation of how NASA scientists have been able to reconstruct the image of that star-forming region is distorted by the fact that it passes by the cluster of galaxies. So what you see is an initial image giving off radiation. The light from that image passes by the cluster of galaxies, and as it is passing by, it is warped, and it goes from a fairly square image at the beginning to one in which it is distorted into this little ellipse. Here is another image. This is a reconstruction, once again, of what would happen if we were able to violate all the laws of physics, move faster than the speed of light, and travel from us here on Earth back to that star-forming region, going by the cluster of galaxies. What you see at the first is the cluster of galaxies with the star-forming region in the background. It's distorted into a little ellipse. And as you zoom past the cluster, what you see revealed is the original shape of the star-forming region, which was actually closer to a rectangular shape than to this ellipse. So you see that the effect of the cluster of galaxies acting as a gravitational lens is to change the shape of the background star-forming region. If you have enough examples of that, you can reconstruct how much gravity there was in the cluster. So here is a more typical example of what you actually see with data. Here is a cluster of galaxies once again. We've already seen this picture, but now we want to look closely at this picture. In particular, we want to look at the tiny galaxies on the outskirts of this cluster. Many of these galaxies are not in the cluster themselves, they are in the background. They're behind the cluster, and their light is passing next to it on their way to us. So what you see if you look at the galaxies in the background is there's a systematic alignment. You see circles. There are regions of galaxies that are all little arcs, and these arcs all wrap around the original cluster. That is the distorting effect of the gravitational lensing caused by the heavy gravitational field of all the mass in the cluster. You can see the number of arcs, you can see the amount by which they're distorted. If there were only one of them there, it might just be that that galaxy looked like an arc all by itself. But if there are many, many of them, there shouldn't be any reason why galaxies are lining up in little arcs, especially if they are at different redshifts themselves. The reason why we see these little arcs is because of the lensing effect of the cluster. And we know enough to take that data, the number of arcs and their distortions on the sky, and reconstruct from it the total gravitational field of the cluster of galaxies. So you will not be surprised to hear the answer, I hope, which is that the total amount of mass you need to explain the amount of gravitational lensing is 5 times as much as the amount of ordinary matter in this cluster of galaxies. In other words, the total mass that we've reconstructed by dynamical mechanisms, looking at moving galaxies and moving gas, matches, is in correspondence with the total amount of mass that is implied by gravitational lensing observations. So this is nice. This is telling us that we're on the right track. If we didn't get that answer, it would have been very interesting. What if you had weighed these clusters of galaxies using 2 very different methods, but you're trying to measure the same quantity, and you'd gotten a different answer? That would mean that you didn't understand something. You didn't understand either something about clusters of galaxies, or you didn't understand something about gravity or general relativity or something like that. The fact that the 2 methods agree and give us the same answer for the masses of these clusters of galaxies seems to imply that we are on the right track. you can never be 100% sure that you are on the right track. It is always possible that you're being tricked one way or another. What happens is, as you collect more data, get more examples of what is going on, the chances that you are being tricked get smaller and smaller. At some point, it becomes a waste of your time to contemplate that you are being tricked, and you should just say, well, now I have found something. There are enough independent things pointing to the existence of dark matter in clusters of galaxies that we've reached the point where either we should say that the dark matter really does exist, or something even more profound is going on, something with gravity itself. So let me look at one pretty picture and then one profound example. Both of these are hot off the presses new results in cosmology. The pretty picture is a three-dimensional map of the dark matter distribution in one direction of the sky. This is from the COSMOS survey undertaken by NASA, and basically what they did is they said, let's take every telescope we have in all the different wavelengths of the electromagnetic spectrum and point them at the same region of the sky. So they took images with the Hubble Space Telescope, they took images in X-rays, they took infrared images, radio telescopes, ultraviolet images, and they tried to reconstruct not just the picture of the sky in one direction, but the entire three-dimensional distribution of stuff. They have both the redshifts to different objects and the images at each redshift. So what they can do from that is reconstruct where the dark matter is. And it's a little bit of a rough reconstruction. It's not highly precise, but you see the answer in this picture. There's a distribution of dark matter throughout space. The distribution more or less matches where we see the ordinary matter. It matches it more than well enough that we can say we're on the right track. What we think is where the dark matter is where it should be. On the other hand, it doesn't match it perfectly. So right now, one of the hot topics in research on things like this is asking, are the things that we see, which indicate that there is dark matter in a place where there is not a bunch of ordinary matter, an indication of some novel mechanism in the evolution of galaxies and clusters that removes ordinary matter from dark matter, or is it just that the data are not very good yet? This is a kind of thing where we really don't know the answer to that yet. We're at the point where we do have a belief, a strong belief that there is something called dark matter, but the detailed dynamics of the dark matter and how it evolves along with the ordinary matter is something we don't yet fully understand. There's a lot more work to be done in that direction. Now let me show you, this is my favorite example. This is something called the Bullet Cluster of Galaxies, and it's a sequence of images of the same object using different techniques. So the first image is just a picture from the Hubble Space Telescope of this bullet cluster. And if you stare at it long enough, and you're a professional observational cosmologist, you look at this picture and you go, aha, that is actually two clusters of galaxies. There's a large concentration of galaxies on the left-hand side of the picture. On the right-hand side, a little bit up, there's a slightly smaller concentration of galaxies. So you can actually take the redshifts of these galaxies, and you can show they really are associated with each other. They are gravitationally bound. These are not just a chance superposition of galaxies at different distances. So this is an interesting example of a double cluster of galaxies. There are two more or less independent objects, but they're at the same redshift. They're right next to each other, cosmologically speaking. So remember, we said that when we just think about ordinary matter in clusters of galaxies, forgetting for the moment about dark matter, in a cluster of galaxies, even the ordinary matter is mostly in between the galaxies. It's mostly in the form of hot X-ray gas that is not concentrated in the galaxies themselves. Something like 2/3 or 3/4 of the ordinary matter is in this hot gas. So when you see a cluster like this, especially one with an interesting shape, it's fun to take a picture of that cluster in X-rays and see where most of the ordinary matter is. So the next image shows us in pink an X-ray image of the bullet cluster, a picture of where the ordinary matter is. The ordinary matter is glowing in X-rays, and what you see is actually quite remarkable. The place where the ordinary matter is, shining in X-rays, is displaced from where the galaxies are. The ordinary matter is also coming in two clumps, just like the galaxies are, but it's in between the two clusters of visible galaxies. Somehow, the location of where the ordinary matter is, where most of the hydrogen and hot gas in this cluster is not in the same location as where the galaxies are. So this is interesting, but it is not a complete mystery. There's a very simple explanation for how this could come to be. The explanation is that in the recent cosmological past, these two clusters of galaxies collided and they went right through each other. You have to think sort of separately about the dynamics of the individual galaxies and the dynamics of the hot gas in between. The galaxies are fairly sparsely spread through the cluster. If you take the total area that you see in a galaxy, it's only a tiny fraction of the size of the cluster as a whole. So when these two clusters went right through each other, came out the other side, the individual galaxies didn't even notice. The individual galaxies just went from one side and came out the other one. You started with two groups, and you ended up with two groups, perfectly separate. However, the hot X-ray gas inside these clusters of galaxies does notice the hot X-ray gas inside the other one. So when these two groups come together, these two clusters, and collide, there is a shock front set up in the hot X-ray gas. The gas is slowed down from moving by the fact that it is interacting with the gas in the other cluster. So what you see is basically the gas gets stuck in between, and you get a separation between where the galaxies are and where the gas is in between. That is, of course, intrinsically interesting to astronomers. Astronomers would like to understand how clusters have evolved in cosmological history. You don't get many examples of two clusters of galaxies passing through each other, so it's a lot of fun just to think about that. But also, from our point of view, we're interested in dark matter and dark energy. This provides a unique opportunity to ask, what does the dark matter behave like? If we believe that there really is dark matter in these clusters of galaxies, one of the features of dark matter is that it doesn't interact very much. The fact that it doesn't interact very much is most obviously displayed by the fact that the dark matter is dark. Most of the interactions over cosmological length scales in things in the universe are either through gravity, which affects everything, or through electricity and magnetism, which affects charged particles. So even atoms, which are neutral, are made of charged particles. That's why we can see them. Dark matter is not charged, otherwise it would be easy to see. They would not be dark. So the dark matter, to a very good approximation, is collisionless. Dark matter particles go right through each other. They do not bump into each other. That's the reason why in an individual galaxy, the dark matter halo is some big puffy thing. The bright visible stars have condensed and settled into the middle of this halo because ordinary matter can bump into other ordinary matter, cool off, and settle down to the middle. Dark matter falls into a galaxy and just passes right through. The dark matter ends up in a big puffy cloud where the ordinary matter settles into the middle. So what we want to know is, where is the dark matter in the bullet cluster? We started with two separate clusters. Both of them had ordinary matter and dark matter. They passed through. The hot gas got stuck in the middle. What did the dark matter do? So the next image is a reconstruction based on data of where the dark matter is in the bullet cluster. In particular, it's a reconstruction of where the gravitational field is in the bullet cluster based on gravitational lensing observations in the background. What you see is quite remarkable. The dark matter, or at least the gravitational field in the bullet cluster, is centered on where the galaxies are. But remember, the galaxies are not centered on where most of the mass is. Most of the mass is in the hot gas in between the galaxies, and it was displaced. But the gravitational field stuck along with the galaxies. So if you look at the next picture, we've superimposed where the gravity is and where the matter is. The gravity is in blue, the matter is in pink, the matter is giving off these hot X-rays. We see a very clear example of where the gravitational field in this cosmological object is pointing in a different direction than where most of the matter is, most of the ordinary matter. That can't be explained if you don't believe in dark matter. If you only believed in ordinary matter, the stuff that is causing the gravity is the ordinary matter. So the stuff where the gravitational field is should be where the ordinary matter is. In fact, this is not only good evidence that there is dark matter in the sense that there's a lot more stuff there than what we see, it's also good evidence that we're on the right track when it comes to gravity. Up until now, we could always have believed that the reason why the gravitational field in an individual galaxy or in a cluster of galaxies is stronger than it should be is because we didn't quite understand how gravity was working on very large scales. Einstein and Newton were somehow going wrong on the scales associated with clusters and with individual galaxies. This bullet cluster result is telling us that that's not right, that there is no way to understand how the gravity could be pointing in a different direction than the ordinary matter if there was just a modified theory of gravity, if there was no actual dark matter. So we'll discuss that result a lot more in subsequent lectures when we're seeing whether or not you can get rid of dark matter and dark energy by modifying gravity. But right now, we're confident enough to move on with the conclusion that there really is a lot of dark matter in our universe.